as far as 8,000 meters below the surface at the bottom of the ocean. In total, around 350 cables, totaling nearly 900,000 kilometers in length, have been sunk to the bottom of the ocean to carry all of our internet traffic. That's enough cable to go 22.5 times around the equator, or more than enough to make it to the moon and back. But here's something amazing. The undersea wires that form the backbone of the internet across the oceans are only the width of a human hair. And as unbelievable as that may sound, it's true. In fact, it's only by using minutely thin fiber optic cables that the vast quantities of internet data are even able to cross the seas. Yep, you heard me right. Fiber optics, same as this. These tiny glass threads are shaped in such a way that any light shone along them stays inside thanks to something called total internal reflection.
That's wonderful. The light follows the liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection. As the light enters the stream, it is reflected as soon as it hits the interface between air and liquid. You can see here the first reflection, and then the second, and the third. This occurs because there's a difference between the index of refraction of the guide material, here propylene glycol, and the outside, air in this case. Recall that any time light strikes a surface, it can either be absorbed by the material, reflected from it, or pass into and through it. The latter we call refraction. It's easier to see from a top view. Reflection and refraction can happen at the same time, but if a light ray hits the surface at an angle greater than the critical angle, it will be completely reflected and not refracted. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection. To create this same effect in an optical fiber, engineers create a core of glass, usually pure silicon dioxide, and an outside layer called cladding, which they also typically make from silicon dioxide, but with bits of boron or germanium to decrease its index of refraction. A 1% difference is enough to make a fiber work.
Actually, what that neat bit of physics means is that the fiber optic thread can bend and flex as much as it likes, but the light will always bounce its way along inside and come out the other end the same as it was when it went in. Using lasers in this way means that all of our data can be transmitted by simply switching the light on and off really, really fast to give the continuous stream of ones and zeros that make up the data that we send and receive every day. It's a bit faster than that. The neat thing is that sending different wavelengths of light and different laser orientations down the fiber, you can have loads of different information streams all flowing at once. They're so effective that a single hair-thin fiber can transmit up to 10 gigabits a second. That's enough to stream 10,000 videos at once, all through just one of these. Mad. Each undersea cable doesn't just have one optical fiber though. By bundling several together, you can get even more data flow, and in two directions too, meaning an entire country could make phone calls at once through a single cable. But the fibers can't just be sunk naked to the bottom of the ocean. They are incredibly fragile and incredibly precious. So engineers go to great lengths to make sure that they are protected from whatever the ocean can throw at them. They're coated in layer upon layer of all sorts of materials, including metal tubing to stop the cable kinking, plastic and rubber to keep out the salt water, and steel strands, and even Kevlar-like strapping to protect from cuts and breakages. By the time you've added all of that, communications cables go from a fraction of a millimeter in diameter to roughly the width of a garden hose. Oh, and it's no simple task to get the cables down there either. They're plugged in at landing stations on the shore and floated into position on the surface before sections are dropped and buried beneath the ocean's sediment. Then, special cable-laying ships with massive spools of cable tow a submersible plough that digs a trench, plops the wire in as it unwinds from the ship. Amplifiers are put in every 50 kilometers or so to boost the data signal, and ships will often work from each end to join the cable in the middle. The roots of these internet lifelines are no accident either. They are carefully planned to pass across some of the flattest and most geologically stable terrain, and there is of course some slack built in to allow for shifts in the seafloor during earthquakes. Still, there's no escaping the many risks that these all-important cables face, from the mundane, like anchors accidentally tearing across them, to the ridiculous, like sharks. Yes, sharks occasionally munch on our internet cables. Since an entire country's connection to the rest of the world can rely on just a few delicate fibres, a breakage, whether accidental or intentional, can majorly disrupt internet traffic, literally cutting them off for about 5 days while a repair ship finds and fixes the problem. That is an awfully long time to go without the internet. I can barely last half an hour.